Alright, welcome to lesson 2. So today we're going to learn a new rule called the chain rule, and it's going to kind of play off the work we've done with the power rule, and that should help it make a good bit of sense, and it will be very, very useful. We'll actually use the chain rule later on in the unit where we'll define it a little more thoroughly and apply it to a greater set of functions. But for now, we're just going to apply it to polynomial functions. Okay, so this situation probably will seem a little familiar, also a little bit different, and that's kind of the point. Given the function y equals 3x minus 5 squared, answer the following. So I'll just explain the first part very quickly. Jimmy wants to find the derivative of y with respect to x, or dy dx. So he uses the power rule and finds that dy dx is equal to 2 times 3x minus 5, right? By taking the taking the exponent, multiplying it out by the coefficient, and decreasing the exponent by 1, which is equal to 6x minus 10. Do you think he's correct? Explain why or why not. So give it some thought, really think about what dy dx means, and whether or not this is the correct way to calculate the derivative of y. And then, once you've done that, go ahead and follow through with B and C. Give each a good amount of thought, and then we'll talk briefly. All right. The first thing to think about is whether or not this application of the power rule seems legitimate. And it certainly seems legitimate in that he followed the power rule correctly. We have something squared, so when we take the derivative of this something that's squared, which is in terms of x, we're going to take the exponent, multiply it by the coefficient, and decrease the exponent by 1, which he has done. But now let's consider whether or not this makes sense for this particular function here. You'll notice that this looks a little different than what we're used to dealing with. For example, when we've had something squared, it's been x squared. And if I take the derivative with respect to x of x squared, well, the power rule tells me that's 2x. But notice here that what is being squared has a few things going on with it. And so maybe it won't make the most sense to just apply the power rule, because there also might be some way in which y is changing with respect to this interior part, right? Notice that here it's just x. Every time x increases by 1, this inner part is just increasing by 1, right? This x just goes up by 1. But here every time x goes up by 1, it's going to be multiplied by 3, subtracted by 5. There's a little more going on. So we might conclude that there's something missing. So then in part B, we're going to square the binomial out and take the derivative. And if we do this, we'll find that we get something that we are much more familiar with. We'll get 9x squared, and then you'll have a 3x times a negative 5, which will be negative 15. You'll have two of those, so it'll be negative 30x plus 25. Now, if you take the derivative with respect to x of this function, you get that dy dx is equal to, and here you'll get 18x minus 30. Interesting, because we can be pretty confident that this is correct, because we know some hard and fast rules that we've proven which allow us to take the derivative of this function. And we got 18x minus 30, which is a little different than what Jimmy got. So what do you think is missing here? Well, we can just compare the two. What's missing? How would you manipulate what he did to get what we actually got and know to be true? Well, it should be pretty obvious that this here needs to be multiplied by 3 in order to get the true change in y with respect to x. So what's missing is that there somehow needs to be, in my taking of the derivative, I need to be multiplying by 3. And why do you think that is? I want to point you to what we talked about previously, which is this interior part. This inside, this piece that is actually being squared, what's the derivative of this piece? Well, notice every time x increases by 1, we actually have a slope of 3, right? The output will increase by 3. And so what we need to find a way is to incorporate this derivative of the inside along with the derivative of the outside, which we're using the power rule to find, so that we can incorporate both pieces to get the true derivative. So let's take a look at C, and hopefully this will make it a little more clear. We notice that the function y is actually a composite function, where f of x is x squared and g of x is 3x minus 5. And so notice f of g of x is going to be 3x minus 5 all squared. So how would you find dy dx in terms of these two? Well, notice that what we talked about is how you can use the power rule on the whole thing, but then you need to incorporate the derivative of what's inside, what's actually being squared, so that you can incorporate all of the different changes that affect y in terms of x. So if we were to write out dy dx, the way that we'd want to write this is that we take the derivative of the whole thing, right? F of g of x, everything that's being squared, and we can do that using the power rule, right? Because what you do is you just multiply out the exponent by the coefficient and decrease the exponent by 1. So what that will be is f prime, where the input of your function f is g of x. That takes the derivative. That's what Jimmy did to begin with. He just took the derivative of the whole thing using the power rule. But then we found that we need to incorporate also what the derivative of the inside piece is. In other words, the derivative of g of x. And we need to multiply that. G prime of x. And this is the power rule. Okay? And it works very nicely for polynomials where they're written in this form. And if you wanted to square this out, you could. But imagine if your exponent was a lot bigger, right? You're not going to want to cube that out if that was 3x minus 5 cubed. And so we can apply this rule, which is called the chain rule. And we're going to actually apply the chain rule to a broader set of functions later on, but for now, we can apply it to these polynomial functions. All right, so here is the chain rule, and we're just going to apply it to polynomials first, so it won't be quite as big as the next time we see it when we'll apply it to a bunch of different functions. But given a function where y, this function y, is a composite function of f composed with g, or f of g of x, where f and g are both differentiable at x, meaning you could find the derivatives of each of these on their own. The function y is also differentiable at x, and you can find the derivative of y with respect to x using the chain rule, where you take the derivative of the outside function with respect to the inside function, and then you take the derivative of the inside function with respect to x. And so in practice, in our examples that we're going to see, we can apply this to finding the derivative of polynomial functions of this form, where you have some polynomial, you have some function g of x being raised to some power n. And what you can do here is notice that the outside function is f of g of x, right? Where the outside function is taking some function g of x and raising it to the nth power. And the inside function is just whatever g of x happens to be. And so dy dx, you're going to take the derivative of the outside function, which is raising to the nth power, and you can do that, multiply by n, and decrease the exponent by 1. And then you have to multiply by the derivative of the inside piece, which is g of x. Take the derivative of g of x. And so this is how we will apply the chain rule for polynomials. So let's go ahead and give a couple some practice, and then we can implement them on our own. All right, so here are a couple problems for you to work on. What you should do is write both these down and try them first on your own, applying the chain rule, and then go ahead and press play and we can talk about it. All right, so notice that this is set up perfectly for the chain rule because what we have is a composite function. First and foremost, we are squaring something, right? That's the, if you will, the f of x. And we're squaring another function, which is your g of x, right? 3x squared plus 1. And so the derivative of this function with respect to x has to incorporate both the derivative of the outside, which is found using the power rule, 2 times 3x squared plus 1. The new exponent is 1. And then we also have to multiply by the derivative of whatever's inside. Well, the derivative of what's inside, taking the derivative of 3x squared plus 1, the derivative of this will be 6x, and this will be 0. So we have times 6x. And so the derivative, I can simplify this all out, and what I'll need to do is distribute the 2 and then multiply by 6x. So if I distribute the 2, I get 6x squared times 6x, which will be 36x cubed. And then distribute the 2 times 1, which is 2, times 6x, which will be 12x. Okay. And so now to check your work, you could actually square this out and take the derivative of the squared out function, which will be much easier to do because you already have the know how to use the power rule to find the derivative of that. Here I've squared it out, and I get 9x to the fourth plus 6x squared plus 1. And we can take the derivative of each piece on its own using the power rule. So the derivative of 9x to the fourth will be 4 times 9, which is 36, x to the third. And the derivative of 6x squared will be 2 times 6, which is 12, x. And so you notice that we get the same derivative each way, which should confirm your solution. So now let's take a look at the next function, and what you'll notice here is that this really has an exponent of 1, and so that should make it a little easier to apply our chain rule. We can take the derivative of y with respect to x, and what we first want to do is notice the outside function, which is just raising something to the first power. It's not a big deal. So when we apply the power rule to the outside function, we multiply by 1 and decrease the exponent by 1. So we'll have 1 times 2, which is 2, and then 3x minus 1. But notice I have to decrease the exponent from 1 to 0, and then multiply by the exponent of the inside, the derivative of the inside, which is the derivative of 3x minus 1, which is just 3. Now notice anything to the 0 is just going to be 1, so I have 2 times 1 times 3, which is going to be 6. Now if I were to multiply this whole thing out, notice that I would get 6x minus 2. And if I took the derivative of y with respect to x, then I would end up with 6. And so we should be pretty confident that the chain rule will work in these situations. All right, I'm going to give you a few more to practice on your own, and we'll discuss them in class. All right, so go ahead and answer these and be prepared to present your solutions.